Hello and welcome back to another video on optics. Today we're going to take a look at the topic of optics called total internal reflection. This topic is a very interesting topic that you usually learn after learning about refraction and some simple laws of reflection when going through the optics chapter. And it's really useful in a lot of different exams, for example, in IB, A-levels, or IMath, and some other university entrance examinations. Now, let's go ahead. I've prepared three diagrams for you where light is going from a more dense medium, such as water, into something that's less dense. As you can see, I've actually set that the index of refraction for air is 1 and for water is 1.33. Now, if you don't know what the index of refraction is, it's just sort of something that shows you how dense that material is. The higher it is, the denser the medium is, and the slower light travels in that medium. You can find the index of refraction simply by dividing c, which is the speed of light in a vacuum or air, something around 3 times 10 to the power of 8 meters per second, by the speed of light in that new medium. And then by dividing these, you get a ratio, which is known as the index of refraction. Now, let's go ahead and take a look at our new lesson for today. So, let's say a ray of light, for example, in picture A, is going from water to air. Now, we know that water is more dense than air, so the ray of light is definitely going to speed up. If a ray of light speeds up, it happens in a way in which the light actually bends away from the normal line, and it goes away, like this. So this is known as refraction. We know that the bending of light, whether going away from the normal line or bending towards the normal line, is known as refraction. So we're going to have a second angle here called theta 2. Over here, we can actually apply the normal angles of normal sort of scenarios of Snell's law, and we can just say n1 sinus of theta 1 equals to n2 sinus of theta 2. We can solve for n2, we can solve for sinus of 2, theta 2, we can solve for anything we need. That's true as long as the angle of incidence is less than something known as the critical angle. So if this is the case, you will have refraction. However, it turns out that at a specific angle known as the critical angle, so if this theta 1, if this angle of incidence or the ray of light going from water into air reaches the critical angle, at that specific angle, the ray of light is no longer refracted, but it is indeed going to bend at a 90-degree angle. So, if the angle of incidence is able to reach this angle called the critical angle, which is different for different mediums, and somehow match that, then it's not going to get refracted. So the critical angle is the angle at which the ray of light is refracted at 90 degrees. The incident light will be refracted at 90 degrees. Is it going to happen if we're going from a less dense medium to a more dense medium? Never. This only happens when we're going from a more dense medium to a less dense medium. So that means that the index of refraction of the first medium always has to be greater than the index of refraction of the second medium. And also the speed of the light is always greater in the first medium than the speed of light in the second medium. Now, in the third and final picture, this is where the fun begins, and this is the part where the ray of light does something amazing. So if the ray of light matches that critical angle and just increases the angle of incidence by a tiny bit more, it's no longer going to be refracted at 90 degrees or refracted at all. In fact, it's going to get reflected. This phenomenon is known as total internal reflection. And total internal reflection is when the angle of incidence becomes equal. It's when the angle of incidence becomes greater than the critical angle. And at that point, we no longer have refraction. We have reflection, known as total internal reflection. So if this is the case, then we can come up with a new formula for calculating the angles. And that formula is n1 sinus of theta 1 equals to n2. We know the ray of light at the critical angle gets refracted or reflected at 90 degrees, right? So we can say n2 times sinus of 90. Now we know the sinus of 90 is 1. So we can actually calculate the critical angle for any medium, the theta c or theta 1, by doing the following. So we can say sinus of theta 2 is equal to 90. And so theta c, or the first theta, is going to be equal to our critical angle. So we can find the critical angle by rearranging this formula for theta 1. So we can say that the sinus of theta 1 is equal to n2 over n1. And so theta 1, which is theta c, or the critical angle, is simply the sinus inverse of the critical angle of the second medium, which is usually air. And if in that case, it would be 1 over the critical angle of the first medium, which is the more dense medium, N1. So you can find the critical angle by using this formula.